To talk about, so the title of my talk, it's one of these many TBA talks on TBA. It's on the interaction of between planetary scale flow and convection. And we did that in a set of, I did that work with my collaborators here that are listed. What is the guy work? Oops. How does this? Or maybe I'll just. Okay, so I'll do. So Joanna Slawinska was a postdoc at New York University working with Andy and myself. Aga Mroviek, who's a postdoc at NASA GIS, and then my two collaborators here in the room, Andy and Wojtek. Oh, thank you. Okay. And so the motivation for the work is to do basically the broad question. If we look at the atmospheric circulation, there is multiple scale involved with it. And we have circulation on the planetary scale, synoptic scale, mesoscale, and actually a lot of convection. And all these scales interact in a very complex manner. These interactions are very difficult to diagnose in general. And so if you try to do that with basically observation, we usually lack the amount of observation necessary to look at the detailed interaction, especially if we talk about convection. We have very little information at the convective scale. And in particular, if we try to figure out how they interact with large-scale motion. And if you try to look at laboratory setup, for example, it's very hard to do anything like moist convection in a laboratory condition, simply because we cannot do the condensation associated with the adiabatic expansion that we see in the atmosphere in a laboratory context. So one way around that is to basically do that in simulation, and in doing simulation that are not necessarily meant to be the most accurate representation of the atmosphere, but actually to do some form of idealized, very highly idealized simulation. And in this case, it would be a very idealized simulation of a tropical Walker circulation, and so on. The advantage of the numerical simulation is that you can basically look, you can measure whatever you need to measure, and you can in this case, you can take advantage of the fact that the computer has become big enough that we can actually do now simulation that span multiple scale, and so look at the interaction between very small scale like convection and planetary scale circulation. So in this talk, I will first report a set of idealized Walker circulation, and this circulation I'll emphasize the fact that they show a very interesting low frequency variability. And so I'll talk about both the mean state and the variability of that Walker circulation, and how it's related actually to variability of the convection. And then I would like to talk a little bit about convection and this idea of using what we call isentropic analysis to actually look at convective motion. And it's both it's a new application of an old idea, and so I will talk about that, and then I'll discuss basically how we can use this technique to diagnose the interaction of convection and the large-scale circulation in these high-resolution simulations. Okay, so idealized Walker circulation. What we did, we took the oil-like model from NCAR, which is basically the small Archimedes group at NCAR, and so we run it in a 2D convection. So it's not exactly this. That's a heavy simplification, but we run it at cloud resolving scale. So basically 2 kilometer resolution, but over a very large domain, so 40,000 kilometer domain. So we can basically span all the way, in this case, all the way from basically convective scale to all the way to planetary scale. And then to get a kind of planetary scale circulation, we just make a very simple setup where we put a SSE fluctuation at the surface. So where we have a maximum SST at 300 Kelvin, 203 Kelvin at the center, and then cold water on the side. And we perform a fairly long interaction over a few hundred days to basically look at what happened and get a nice steady state in the variability. So this is an animation of the zonal wind, so the wind in the x direction. So this is a 40,000 kilometer domain. This is all the depth of the troposphere in this case. So the model goes higher up, but we didn't show up. And so you see red is positive value, blue is the negative value. And so you see essentially the warm water is over there, the cold water is over there. And so you see that circulation that basically look like a direct circulation, inflow at low level, outflow at upper level. And so if you try to visually make an average of the movie, it does look like you have a mean overturning circulation. But of course, this circulation is anything but steady. It's basically fluctuating. It's fluctuating on multiple scales. You see bursts of convection. You see sometimes reversal of the circulation within the center. You see all kind of things. You can see also that in addition to have this big overturning circulation associated low level inflow, upper level outflow, you find occurrence of these low mid-tropospheric jets, so sitting above the boundary layer, but giving a big inflow into the convective region. So this is that, and we have like 270 days of that thing so going on, and so showing all that kind of fluctuation. The first thing to mention is that if we just take the simulation, we mathematically it's hard to do visually, but mathematically you just average things out. So this is the circulation we get. So we get a mean Walker circulation, so we have the cold water here, warm water here, so we get a fairly moist region at the center of the domain, and then of course over the warm water we have a shallow boundary layer and a fairly dry, very dry free troposphere over here. If you look at the circulation associated with it, you see that it exhibits this direct overturning circulation, so air rising up, so this is zonal wind, so air rising up here in the convergence, low-level convergence, upper-level divergence, so we have this overturning circulation. One thing that is worth emphasizing is the structure of the circulation, as I pointed out, in the mean, so it has both that upper-level, upper tropospheric outflow, but there's an inflow both at the lower level, at the surface, and an inflow also in the mid-troposphere. If we go back, I'll talk a little about this. So the quantity, so this to show here on the right-hand side is basically the condensation, the cloud condensate to show the distribution of cloud. So associated with this warm water and this ascending of the warm water, there is a region of essentially high cloudiness, deep convection, and so on that's going up there. And you see cloudiness, it doesn't mean that the subsidence region are cloud-free. There's cloud, but they're basically limited to relatively shallow convection and some little congestion over there. On the left-hand side is one of my favorite quantities, basically the equivalent potential temperature. And so essentially what you see is a classic structure in the tropic. If you look at just the horizontal mean, so you have high value of the equivalent potential temperature. By the way, I assume that, I don't know how many mathematicians we have versus atmospheric scientists. I assume that when I say equivalent potential temperature, everyone is happy with that. Everyone is happy with? Okay. So I'll keep that. So we have I theta E, I equivalent potential temperature in the surface, I equivalent potentials above. In the moist region, the convective region, we have a minimum of equivalent potential temperature in mid-troposphere, but the mid-troposphere is fairly moist. We see the minimum is maybe 10 degrees Kelvin less than one we see at the surface and tropopause. But then if you look in the subsidence region, we have this very low value associated with this very dry subsidence region. So we have this structure. Nothing of that is what it's pretty much what you would expect. It seems fairly realistic, except maybe for the very dry air over there. Okay. So now the interesting part is basically what is the structure, what is the low frequency variability. On the animation, you see this pulsating and so on, and it's pulsating on a lot of different scales. What we like about this simulation is that it does show a variability, and so this is cloud top temperature. We just use that to kind of show a little bit more the detail. So the low value corresponds to very high convection stratiform clouds, and you see these bursts of convection at various scale. And so this is 40,000 kilometer domain. So this guy has sometimes synoptic scale or mesoscale cluster, or sometimes even smaller scale going on. And so what you see is that over that time, that 270 days, you basically see this period where you have these bursts of extended region of convection and then compression, and then so the convection kind of expand, compress, and there is a fluctuation of the convective activity all over that. The time scale about this guy, if you look about it varies from case to case, but there is a variability of about 20-day time scale. So kind of intraseasonal, not as a little bit shorter than what you would want for something like the MJO, but I guess on the time scale of monsoon breaking things.
Well, you can argue the Walker cell is is going on one-half the domain, and that's 20,000 kilometers, not 40,000. So 20 days is good for 20,000 kilometers.
Okay, I wouldn't agree with that, but you're free.
40 days for 40,000.
Yeah, so maybe it's just propagated. Yes, but it's a 20 days rather. Yes, but it's on the roughly on low frequency variability. Okay. So what we did for the analysis is so we basically did a relatively straightforward EOF analysis. So we took, in this case, the surface wind, so the wind at 500 meters at the lowest model level. So you should see here, which basically so in the alternance between region period was a very strong low level convergence, and then period where basically the Walker circulation almost disappeared completely, at least at the surface. So we do an EOF analysis, so that's the first EOF that comes up from the surface wind, and this is the principal component associated with that, which basically over these 270 days shows this up and down, this fluctuation of the surface wind of the Walker circulation, giving you about a 20-day peak frequency over there. And then, of course, to get a little bit of a better idea, of what's happening in the frequency variability, we did a succession of lag regression of all the various fields. So now we have a principal component index, and we can just do linear regression on any kind of field we consider. And so just to show here, so we have three different fields. Here's the surface wind, so the zonal wind. So basically at lag 0, it's where we have the full PC. And what you see is basically associated with the peak intensity of the principal component. 10 days before that, we have a very weak Walker circulation. This Walker circulation intensifies, and then 10 days after, basically the circulation has weakened. So that's just coming from a lag regression. It's consistent with this frequency of about 10 days. By the way, this guy, for these, it's always I'm showing you in this case the mean plus the principal component plus the lag regression. So it's the mean plus the lag regression, not simply the anomaly. So in this other case is basically the same thing, but now it's with the precipitation. So associated with the fluctuation of the Walker circulation, we see that we have this peak of the precipitation, basically that's at lag 0, and actually the peak precipitation follow the peak of the surface wind. So part of it, there's a lag. And the other thing that is interesting in that structure is that actually the precipitation, the peak of the precipitation is not at the center over the warmest SST, but it's actually mostly on the edge of the precipitation region. So the peak precipitation occurs where you have the strong inflow, and that's where you see the maximum precipitation on the side where you have the inflow of moisture that goes up. You don't, but the advection never makes it really, doesn't really enhance the precipitation in the center. And then the shutdown, the suppressed period here is kind of a very weak precipitation overall and very narrow precipitation region. And finally, this is the water content. And so some of the interesting feature of the water content is how it differs actually from the precipitation. So we do have, and in particular what you see with the water content, you see this buildup. So what precedes the peak precipitation in this region is actually a buildup of moisture that's taking place. 5 days prior the maximum surface wind, you have this buildup of moisture in the subsidence region. And basically that moist region start to contract and then give you the big precipitation over there. So now I would like to go a bit to the structure of this oscillation. And so this is the full time evolution. Basically look at the convection here, you can see already in the subsidence region, because we have less subsidence, there's less drying by the subsidence here, and so we have actually a moisture buildup already starting over the cold water. So during that surface phase, actually, that's where the atmosphere is moister in that surface region. If you look 5 days later, as the circulation is still weak. But actually, if you look at the lower level now, the lower level has strengthened. And now the other difference is that, let's go back. So the lower level is weaker, but now we see now that the mid-tropospheric jet, the anomaly in mid-tropospheric jet has reverse signs, so that we are in a period that normally we have stronger, we start to have an inflow in lower level, we start to shut down the inflow in the mid-troposphere. So the flow in this direction is actually weaker, so we shut down the advection of moist air into the precipitation region, of dry air in the mid-troposphere, and then we have a stronger outflow, a weaker outflow over there. In terms of the moisture distribution, you see that we have now a buildup of moisture that we saw just over the very dry water now has basically extended all the way to almost the edge of the precipitation region, and here the anomaly is almost close to 0. And then we get to the active phase, and now in the active phase now we get a very strong overturning circulation, so the Walker circulation intensifies. Again, the structure of the jet is a little bit different, and now we see essentially the moisture that we saw that was building on the side has been advected, and now it's basically found into the precipitation region. You see that the peak precipitation is again occurring on the side of the precipitation region, not at the center. And then because we have this very strong circulation, we're starting to dry out the subsidence region quite a bit. So there's this back and forth going on with the moisture, and then when, yeah? So there's SST with variation, so basically warm water, it's doubly periodic, it's periodic in the x direction, so things can, sorry? So it's a 2D, so there is no y direction. So it's a zonally periodic, so it's a slab of the atmosphere along the equator in that context. Okay. And so now in the decaying phase, what we see is that the circulation weakens. the most interesting signature of the decaying phase is basically again now. So 5 days after the peak circulation, now we see this very strong strengthening of the jet. So we have this airflow at between 4 and 6 kilometers, basically very strong airflow into the precipitation region. And this airflow is, if you look in terms of the distribution of theta E, this is the air with the lowest theta E. So this very low advection, this advection of very low energy air, which contribute to basically cooling down and shutting down the convection in the convective region. And at the same time as this is happening, we basically have this very strong drying of the subsidence region. So that's the point where after basically a period of very strong active water circulation, all the subsidence region dried out on the side. Okay. So this is the structure of this oscillation. Essentially, there is this very strong interaction between the distribution of moisture and the need for the buildup of moisture on the subsidence region that is then being advected by the flow into the precipitation region, and the modulation of convection by also the flow, the mid-tropospheric jet above the boundary layer that basically advect low entropy air into the precipitation region. I just want to point out a few more things about the simulation. So some of it is basically has to do with, so this is now again a zoom on a 50-year period, showing here where we saw the active phase and the suppressed phase based on the principal component. And just to show a little bit the importance also of individual systems, so we have, in this case, we have this fairly large system associated with the expansion of the precipitation zone. We see this very massive system over there. And then we have very different system when we have the compression, so the suppressed phase. We have this system that propagates. So this one system is like a very massive score line moving from the moist region into the dry region, associated with one system doing a lot of the expansion of the precipitation region right there. And then in the compression phase, we have another set of system, which the structure is basically we have an envelope of a much smaller convective system going on over there. So the structure, they seem to be a very complex interaction of both this low frequency variability and the type of convective organization we see. I just want to zoom on an animation of this. So this is essentially zooming on that one system over here. So it is actually the system associated with the expansion, followed by the compression. So you see that one system expanding is associated with here the cloud top temperature. So you have this very strong, almost synoptic scale score line moving to the right, and followed by the compression, where you have this envelope of convection moving in the opposite direction. And this is a surface wind. So you see that associated with this massive score line is this flow with very strong low-level convergence, a very strong jet in the back of the score line, and then inflow of basically dry air from there, and then that thing's collapse about 7 days, and then that thing's moving back. So on the bottom side is just to illustrate a little bit the structure and the smaller scale structure of the system. So this is this one system. So this is the zonal wind where you see the inflow, the back jet, and then the outflow, the inflow from the convection, and so you see the individual convection. Yeah, maybe, yes. Yes. Yes, let's blame Boulet. So this is the equivalent potential temperature. This is the last bit, because there will be a link to the next part I want to talk about. So we have the convection over there. So this is a system. It's progressing. It's actually, when you see what's happening, it's progressing in this region of suppressed convection, where you have some cumulus convection, shallow convection, but you have this very dry mid-troposphere. And as the system approach, you start to have this burst of convection associated with the mesoscale or synoptic scale or system moving in. And you see then these bursts of convection associated with this high theta E air being basically carrying up. And so you close out these bursts of convection, and then the high theta E air basically ending up in the upper troposphere over there, and so forth. You can see also some indication, which is very nice in the simulation, of actually this low theta E air sitting in the mid-troposphere being advected down, so there is re-evaporation of precipitation, bringing this low theta E air down in the boundary layer. And so after the system is passed, actually, this high theta E air here is gone. You'll find it in the upper troposphere and so on. And then this low theta E air has been moved down. It's basically has shut down or removed, has cooled down and dried down the boundary layer beyond the system. So this is the kind of complex interaction and so on. So what is nice about a system like that is basically a model like that is that it exhibits a very rich type of multiple scale interaction. So we have We have a steady the mean Walker circulation. We have low frequency variability. They have mesoscale system. They have convective system. So if you want to try to test ideas about how to deal with this multi-scale, a model like that is not as complex as the real atmosphere. It lacks key physical process, but at the same time, it's a very nice testing ground for all kinds of ideas and so on. And it shows a complexity that is quite remarkable and so on. So now I show you this picture about Decay, and I want to talk about something that's actually. I did all my studies in the U.S., and of course in the U.S. We don't care so much about the tropics, though I do, but a lot of people care about mid-latitudes. The concept of isentropic analysis is an old idea that dates back from Biones, and actually I think it was originally proposed by Prandtl. And so I wonder how much. So if you study in India, how much you care about mid-latitude system, and in particular how much isentropic analysis is something that you discuss on a regular basis. I see some yes, I see some no. Okay. So the basic idea is maybe I can. Or do we have chalk? Oh, perfect. So one of the things that we want to do when we look at the circulation is to try to understand partial trajectories. And so one way to look at partial trajectory, so if you can follow parcels, that's great, but that's very hard to do because you need a lot of observation and it's hard to track in a parcel. The alternative is actually you can do what basically the Professor Narashima showed yesterday. Is you can put dye in a fluid and you follow the evolution of the dye. And so the reason, of course, that we look at the evolution of the dye, because if you look at where the dye is moving, you're basically following parcels which have red dye, parcels which don't have red dye. And so in a way, the idea is that if you have a tracer, and the equation for the tracer is, the tracer is conserved following the evolution of the flow, except for some small diffusion, so you can follow the evolution of that tracer, and following the evolution of the tracer gives you some indication of where the parcels are going. In the atmosphere, we do lack tracers. So, I mean, you could actually, there is some tracer, conveniently, we're polluting enough now that you can actually follow the distribution of pollutants. But in general, there is a lack of tracer. You cannot really set a tracer wherever you want to do. We're not allowed to release red dye, I think, in the atmosphere. However, what nice things about physics is that actually we have a natural tracer that we can use. And it's come from the second law of thermodynamics. So if you write the second law of thermodynamics, second law of thermodynamics tells us that we have a quantity called entropy, which is basically with rate of change given by Q over T plus some kind of irreversible production. So now if we have a system that is adiabatic, so if you assume that the heating is basically not too important, then we have a quantity, and this guy is really relatively small. It's important, but it's small. So we can often neglect that guy. So we have a quantity that acts as a pretty good tracer, and it's called the entropy. So of course, if you're an atmospheric scientist, you say, well, entropy is, I have a problem. I like to talk about entropy, but for some reason, atmospheric scientists don't. Actually, atmospheric scientists talk a lot about entropy. They just don't call it entropy. You call it potential temperature. And so you have potential temperature rather than entropy just because it's the entropy that doesn't bear to say its name. And so you can use potential temperature as a way of tracing air parcels. Now, there is another catch, and is that this conservation, so potential temperature is a good definition for entropy, it's a good measure for entropy, except when you have phase transition. And so whenever you have...
So what happens in phase transition?
So
the idea is diabatic, it flows diabatic.
So actually, my version of entropy includes the contribution of latent heat and so on. So you can define an entropy for a mixture of moisture and water vapor, and you can actually define an entropy that is perfectly conserved when you have phase transition. Actually, there is a second problem. It's actually you can define more than one. There's more than one version of entropy you could use because you can change the reference state that you use to define entropy, except if you want to make use of the third law that no one does in atmospheric science. Well, a few people do, but I don't think it's relevant. So you can define a moist entropy that include the latent heat.
What time of station is it? It's 200 kilometers.
200 kilometers, maybe hundreds of kilometers scale.
I'll get to this figure if you give me a chance. So to finish the part is that if you want to take care of a concept of entropy that include phase transition, you want to use the equivalent potential temperature. There's other that you could use, but the one that is the best for the kind of work that you want to do is basically this equivalent potential temperature. And it's conserved if you have phase transition. There's some issue when it's freezing, but you can even define it for freezing. So now to go back to this kind of work. So the idea was proposed simply that we lack observation for all these complex motions. But we can actually trace them back by following, and there was the work that was done in the 60s and 70s, basically using following air parcels on isentropic surfaces as a way of tracking them down. We don't have the full data, but we can see how the isentropic surface is changing. Now, a lot of the work that is being done is actually being done using potential temperature because it was done in mid-latitude by people who not necessarily paid attention to moisture. They didn't think convection was too important. But actually some did. And actually, if you look back at the original work by Bjerknes, he was paying a lot of attention to moisture, and he actually introduced some of these moist entropy concepts. And this is a paper by Harold, and it's what is called a moist conveyor belt in mid-latitude, and it's basically showing you a mid-latitude system, and it's their interpretation of what happened in the circulation of mid-latitude eddies. And what it shows is that in a mid-latitude storm, you have three main flow. You have an upper tropospheric flow associated with dry air moving. High potential temperature air, but you have a second flow, which is what they call the moist isentropic analysis and this isentropic circulation. Most of the work has shied away from looking at convection. And there is a relatively simple reason for that is that this is a simulation of convection when I show this is one of these isentropic surfaces in a simulation of convection, a three-simulation of convection. What you see is, I apologize for the fact that the animation is very fast, but it's a sequence of deep convection. And so this isentropic surface, if you have theta E, you have a double max, you have a minimum of theta E. Of theta E can be found at the surface and in your upper troposphere. And this is what you see, high value of theta E corresponding to either warm moist air near the surface or actually high potential air in the upper troposphere. And the deep convection in that framework is essentially deep convection is this kind of plume that basically joins these two isentropic surfaces. So one of the difficulty of describing the isentropic circulation in the context is that the surface you're trying to describe is messed up. I mean, it's folded and so on, and it probably, if it's turbulent, it has a very nasty fractal structure and so on. One way around that is basically what I've proposed in a recent paper is basically to resolve that problem by just averaging everything out. And so the idea is to introduce an isentropic averaging, which is basically you look at any latitude, you do a conditional, you do integration on basically all the property of the parcel you're interested. So if you're interested in property F, so you do an integral, multiply that by a delta function. So in effect, you take all your data set, you look at the property F, and you bid in terms of basically height and equivalent potential temperature. And so you can apply that operator for the mass flux. So you can solve the mass flux as a function of height and theta E. And when you do that, you basically can integrate this mass flux to get a stream function. So you just integrate that in terms of theta E, and so you get a stream function. So in practice, what it does is basically this is the mass flux. So this is basically we do in some simulation of convection in radiative convective equilibrium. So we compute this mass flux function Z and theta E. So this air going up, and so you have air going up at high value of theta E. You have air going down in blue over there. The black line is kind of the horizontal mean value. So you see that slow subsidence over there. And then you turn that into a stream function by just taking an integral in the horizontal direction. I just like stream function. I think they're right here. So this is a zoom on that stream function. Of that will give you a mass transport. So this is about 4 kilo per 0.04 kilo per meter square per second. And so the main structure of the stream function, so the stream function is associated with circulation going in that direction. So here air rising at high value of theta E. So warm, moist air going up. And then you have colder, drier air that moves down. Is mostly following the mean state. So it's a slow subsidence in the environment. At the top here, which is very nice, actually you can detect a signature of what we call a convective overshoot. So where you have the deep convection overshoot through the tropopause. So there you have actually air which is slightly colder that rise up and entrain then down air that is warmer. Another very nice feature is actually when you look at the air going up, it's actually, it doesn't go up at constant value of theta e. It's actually, the theta e is moving, is going down as the air rises up. So you can detect the entrainment. You have a signature of entrainment. So as the air goes up, it mixes with the air from the environment, and as a result, the air, the theta e of the updraft goes down. And you have a similar effect. It's actually, as this moisture, the mixing takes place, you have the entrainment of moisture over there that basically is associated with the increase of theta e as the air goes down. And another feature that I very much about this kind of analysis, actually, if you look at the transport, very often when you have convection, you basically have the peak of the transport peak below at low level. So convection force at the surface is not starting in the middle of the troposphere. All the convection, the maximum actually mass transport is at low level. Is associated with a lot of either dry convection below the cloud base or shallow convection above it. You can do other things. I'm running a little bit of time, so I'm going to skip on some detail, but you can use that conditional averaging to identify various things. So in this case, vertical velocity, where you can find actually that some of this ascent is associated with updraft that go up to velocity of 40 meters per second. And you can see actually some of these ascent is associated with very, very even. So all this upward motion occur in maybe less than 1% of the domain. So part of it is this conditional averaging allow you to detect some of this deep convection, which is extremely scarce, extremely rare event, but by averaging, you basically isolate the scarce, the very rare event but they're responsible for a lot of that mass and energy transport. Okay. Last thing is actually after, maybe I'll skip and that's a measure of entrainment. We can get a measure of entrainment, or maybe I'll talk a little bit about it. It's in response to Professor Narashima's talk. It's actually in this analysis we can define an entrainment as a function of theta e and z. And one thing that's interesting is indeed the entrainment goes up as theta e goes up, and this theta e will be basically a measure of how much condensation is taking place as the air goes up. But of course there's two interpretations. Is basically you have more condensation and you have less entrainment, or you have less entrainment and so you have less mixing and so the theta e remains higher. But it goes in the same direction that air where you have more condensation is actually entraining less.
So what is the entrainment scale?
So that's in meters. So it's so I mean, and you should really look more in this region. So it's a few thousand meters. So it's more or less on the scale. It's in on the scale.
The scale that is entraining, or is this?
So it's the rate of it's the d log m dz. D log m dz. So if you so it's the scale is something like, so if you have a plume. No, so it's the scale at which the plume gets diluted by a factor E. It's a dilution rate. There's a rate of dilution, yes. Yes. So you can do this kind of diagnostic on the simulation and do that kind of things. I don't have the explanation for that, but I thought it was interesting in context of yesterday's discussion. Okay. So maybe I'll fast forward a little bit on the thing. So now we have this simulation. We have this tool, and I call isentropic analysis that let me look at convection at the behavior of the transport at convexity scale. I have this big simulation with a lot of variability. And so what we did is basically we take the whole simulation and we separate between large scale and convective scale. So the large scale, we divided the domain in 64 domain. So one of the motivation, we think that given the fact that it's 2D, we wanted a subdomain that was large enough to do a decent averaging. The other reason is 64 was the number of processors we were running the simulation with, and so it was very convenient to do the averaging on that. The scale, so it's turned out to be about 600 kilometers, so it's a little bit of a large mesoscale, but it's for 2D. And so what we do, we compute the average isentropic stream function, and we basically separate between the transport associated with the large scale circulation, so on this 600 kilometer resolution, and what happened at the convective scale. And so this is the full transport in the isentropic stream function, so it's the full transport by circulation, so you can see over there, so you have ascent of I theta E here, you have a lot of circulation over there, and then you have the subsidence, a lot of subsidence of very low theta, very dry in this region, and then you have some mixing over there. If you separate that between the mean, you see this is the mean circulation over there, so giving this ascent, but it's slanted, so as if you look just at the mean circulation, it looks like the air goes up, and after it goes up, it gains theta E, and then goes down in this very dry region, and then move down. And then you have the convection part itself, which is much more of this very upright convection. There's a lot of shallow convection going on. There is this low-level entrainment that you see in the tilt of this thing. And then you see the upright convection. And then you see a fair bit of basically downdraft going on in this region. One thing that is important to remember whenever we talk about the circulation and the global circulation is actually the shear magnitude of this guy. So the mass transport associated with this global scale is about 2×10⁻³ kilo per meter square. The circulation associated with convex scale is 4 or 5 times larger. So whenever we discuss a large-scale circulation, I think it's always important to remember that whatever large-scale circulation you're looking at, average and scale of a GCM scale, it's only a tiny bit of what the atmosphere is doing. It's actually a very small portion. In this case, maybe 20%. It's a little bit more in the upper troposphere. But this large-scale circulation, it's a small fraction of all what the atmosphere does. A lot of what the atmosphere does is actually taking place at a convective scale. And so if you just think of the GCM scale or the scale at the order of 100 kilometers, you're going to miss a lot of what's going on. And a lot of what's going on in a GCM is actually carried through the convective parameterization. And so that's always a cause of concern. So whenever we're looking at climate simulation or even weather forecasting simulation, we're missing a lot of what the atmosphere, or a lot of what the atmosphere does has been parameterized and is not represented in that context. So, perfect. How am I doing on time-wise? Perfect. Timing is remarkably good. So what we did now is we have this convective stream function over there, and we can actually do. We basically have that for 64 grid points in our domain, and we have that for 270 days. We did actually this guy on daily average. We could do shorter time scale and so on, but we just did the first pass through. We choose to do that. So we have about 12,000 time points, and we have these 12,000 basically image, two-dimensional figure. And so we can. The first thing we did a EOF analysis of this guy, and so this you can of course get as many EOF as you want, but we focus here on the first 4, and in a way of looking at these as kind of various convective regimes. So we have this simulation, we have this very long simulation. In a way, these high resolution are very nice, but it's very hard to characterize what convection does. I mean, it does a lot of things. And so this is a way of kind of sorting all this convective activity that we see into different categories. This may not be the best way to do that, but this is our first attempt. So let me walk through to the various EOF, these various convective regimes as we isolate them in this analysis. So the first one, the first EOF, is basically this big structure, and actually this structure is very similar to the mean stream function for convection that we see. And so it's a structure that is associated with ascent of moisture and substitution of dry air. So the positive anomaly is actually the opposite sign of the mean. It's just how it can turn out to the EOF analysis. So the positive value of that EOF, or the principal component, corresponds to a period where it's the stream function. Now it's basically the mean plus one value of the anomaly. And so you see suppressed convection above it, and you get intensification of the shallow convection, or you get convection basically is limited to shallow convection if you have a positive anomaly. If you have a negative anomaly, you basically get this enhanced convection, you get much more convection, and it actually goes slightly higher up. So this first UF really represents a big modulation of convection, more convection, less convection. You can see it over there. You can see actually there's all the basically positive value in the subsystem region where there's no deep convection, and in this region where you see this score line and so on, you see this signature of basically negative anomaly associated with burst of convection precipitation. So this guy looks very much like mean precipitation in domain. So that's but it's nicely captured. You can see it's also very skewed. So the positive value are barely positive. The negative value is extremely negative. So there is that asymmetry that we know. You see the same asymmetry in precipitation, of course. The second mode is quite nice. The second mode, maybe I don't know if it's easier to see. The second mode is actually this is the structure of the anomaly itself. The second mode looks actually like the horizontal derivative of the mean. So it means that if you have a positive anomaly, the positive anomaly corresponds to the same structure of the stream function, but shifted toward higher value of theta e. The negative anomaly corresponds to the same structure of the function, but shift toward lower value of theta e. And so what's happening here, if you look at now the principal component of that period, so it's 40,000 kilometers, the old period, you see that it's actually alternate between big positive value, negative value, positive value. It's basically following the low frequency variability. With a 20-day free variability, we have period where the atmosphere is warmer, period where the atmosphere is colder. And so associated with that, we have actually convection that shift toward higher value of theta E, convection that shift toward lower value of theta E. So this is nicely captured by this basically variation of the value of theta E in the S. And the second mode just look at the deep convection shifting toward warmer and lower value in a very, very nice way. The third and fourth mode, the structure of the third and fourth mode are a little bit different, and in a sense they're not as simple to look at. And if you look at the positive anomaly here for the third mode, negative anomaly, what you see is that this third mode is associated with convection that goes deeper, but the difference here, the width here, is less. So if you take the mean plus the anomaly, you see that this convection with air goes up. The air goes up more vertically, and the air that comes down comes out with higher value of theta E. So it's a situation where you have convection in a moisture environment, where you have less effect of non-treatment. So you have less dilution of theta E as it goes up, and the convection ends up going down, and then the air that comes down is actually more humid, and so as it's marked there. In a negative anomaly, you have air that the convection doesn't go as high, and the tilt here is much more pronounced. So you have convection in a dry environment, basically associated with stronger entrainment, and more basically loss of theta E in the updraft associated with the entrainment of dry air. And if you look at the distribution of the PC in that plot, you see that the positive value associated with basically less impact of entrainment are concentrated in the central region, which is on average moister. So it's the region that is moist. We have less entrainment, and that's nicely captured. When on the side of the precipitation region, we have this situation, we have this more entraining, the effect of entrainment that can be captured on the convection that can be captured on the side. So situation, we have probably like a more congested cloud, more entraining clouds on the side, and more upright convection in the middle. Finally, the last mode, it's a similar situation where there is a positive negative anomaly here. So you see the effect again. The positive anomaly. I need to see. Yes. So you see the circulation. The positive anomaly is also associated with more convection higher up, but then there's more convection actually coming down over there. It's a situation where actually you have more stratiform precipitation and a more mesoscale downdraft. So more air going down, a low value of theta E, and so on. One thing that is interesting that is not obvious just from looking at the picture, you would see it if you could read that number, but that number is much less. So the value is just 6, then minus 3, when the value is minus 9, and this corresponds to the magnitude of the stream function right there near the surface. So in this situation where you have this more unenhanced stratiform convection, you actually less shallow convection below it. So you have this precipitation that's basically bringing cold air down, but it's also shutting down the shallow convection below it. When in this situation you have actually enhanced shallow convection over there, and you see the structure. So you see this enhanced shallow convection in this region, and then you see this localized episode of very intense stratiform convection in the center of the domain. So I think I'm reaching my time limit, so I'm going to skip a little bit this last slide and just bring the conclusion. So I apologize if I present a bit too much, but so what we did is basically we have this benchmark simulation where we look at the interaction of large scale between a Walker circulation and smaller scale. In particular, what's interesting about the simulation, it has a very nice example of low frequency variability that link moisture advection and the structure of the horizontal wind is also quite important. The other part is basically this idea of using isentropic analysis to look at convection. So how do you characterize convective motion in turbulent flow? And so one suggestion is to go back to this old notion of isentropic analysis and to look at the mass transport sorted in terms of theta E. That seems to look that seems to work fairly well to look at convective overturning in that scale. And finally, the last part is so we can use this technique to basically analyze the different convective regime by just statistical analysis as a way of figuring what this convection does in these high-resolution simulations. So as a way of characterizing the interaction of convection and the large scale stuff. Thank you.
We can have some couple of quick questions.
That was a nice simulation. You looked a lot at the thermodynamic aspects, but looking at these propagating superclusters and whatnot,
yes,
there must be enormous amount of momentum transport going on.
Yes.
Have you looked at that?
Yes, we have. Maybe not to the point where I would be fully happy with what we've done, but there's definitely, so I can show you in the paper, we analyze And in these two systems, in this different system, we see in the expansion and contraction, we see different structure for the momentum transport. I also see that Andy wants to make a comment on that.
Well, I was just going to tell you that superconductive system you see actually has, from Liu and Moncrief, a forward tilted upper shear. Yeah. Propagates in a forward tilted
That is generated by the model.
Yeah.
in the model at high levels.
Yeah, well, you're too fast for me, so I'm not sure that I've digested what you said. But let's see, you showed simulations, very interesting simulations, which had, as I saw it, a large number of intermittent convective plumes.
Yes.
And then you average them in some sense, I presume.
Yes.
And are they conditional averages, or are they just averages over the whole field? You have a whole field in which you're generating these.
So the idea of the isentropic averaging, this isentropic analysis, is to do a conditional average.
It's a conditional average.
On entropy.
With entropy as the condition. With
Yes.
entropy, some criterion on the entropy as the
Yes.
condition. Yeah. And because you use entropy as the tracer,
Yeah.
it is in some sense telling you about directly about the transport. Am I correct?
Yes,
It's
so-
visualizing. It's
Yeah.
visualizing. I mean,
Yeah.
you had stream functions and so on.
Yeah.
So if you go back now and look at where you had that entrainment length scale.
Yes.
So what does it say about the entrainment? You have relatively high entrainment lower down in your
Yes.
at relatively low
Yes.
heights,
Yes.
and then
So you have
it drops off to zero. What happens to it later on?
yeah.
Because your plumes seem to taper out.
Yeah.
Your plumes seem to taper out, and from that,
So maybe I can.
I want to know whether when your plumes seem to taper out, that's happening to the whole mass flow, or it's because of the entropy conditioning on the way you trace them. Do you see what I mean?
So I think. So yeah. So I think when you look at the mass flux associated with this plume, if you take that as an average of the mass flux of all the plume, you see that actually there is, on average, the mass flux goes down with height. So on average, there is detrainment at each level, and detrainment
So
is
that average mass flux which is going down with time, what is it? It's not the full mass flow average over all your plumes, or is it that some of the plumes are drying out? See, because this is an average, isn't it?
It is an average, yes, and
Some
you
of
have
the
to be.
plumes may die out, some of them may shoot up, because you had a very interesting picture,
Yes.
visualization
Yes.
of these intermittent plumes rising and
Yeah. So a lot of the plume actually never makes it to the top.
They
A lot of
don't
the
make it to the
plume,
top.
basically, what you see. This,
so at the top, you're actually averaging over a smaller number of plumes.
Yes.
All of that is taken into account, isn't it?
So this show the total mass transport, but then you can do some other. I'm not exactly sure, but this is the number of events, so it's a log of number of events. So when you look at this plume, and some of this plume that goes up fairly upright are very rare. So these are very narrow ascent, very intermittent, but they show up. And one thing I like is that actually this is a way of capturing them, and capturing is very rare event. But these guys are important for the transport of heat all the way in the upper troposphere. These are part of what's going on. But a lot of the plume that you see never makes it to the top, and you see. So they,
That was there in your visualization as well.
yeah, yes.
Your plume areas on the surface are again random in some sense. Does that come out of your equations, or does it?
I mean, the system is turbulent and chaotic, and so it's continually generated, and the simulation is run for many consecutive rotating time. So it's
Very interesting. I mean, I
Yeah.
need to talk to you.
yeah.
Maybe one quick question.
The question is about idealized Walker circulation
Yeah.
and the picture of front that you showed. Question is, what sets the decay time of that front? Because in the animation, I thought it was almost kind of instantaneous. And what sets the width of the front?
Can you clarify a bit the question? So what time scale are you wondering about? Oh, I can bring
The
it up.
decay of the front.
The decay of the wind.
The front that is forming.
The
The front, you
So-
showed a longitude
these kind
time.
of big things, and or the other one.
The other one.
Yeah. So let me. Oh, I see the other movie. Okay, I'll see if I can get to there. So it's not a time scale. At least our interpretations will be different, and it's actually a little bit simpler. So you have these. So I should have explained actually. So this is 8,000 kilometer. This is 6,000 kilometer moving average as things move around. So it's about, I apologize if it was a bit too fast. But so you have these fronts moving, but it's moving from the moist region to a gradually drier environment. And so what's happening is not the thing is decay. It's actually it starts having moisture. So it starts to get over the colder and colder water, and at some point the moisture supply shut down, and you just don't have the energy to shoot more plume, and that's essentially what happened. There is another effect which it's not obvious. I don't know if we will be able to see it on this simulation, but it's also the point where the large-scale circulation starts to shift, and so one of the issues is to which extent the shift of the large-scale circulation is partially tied to that system, but as it happens, we have this mid-tropospheric jet that shows up. And this mid-tropospheric jet is basically going to bring in that low entropy air into the system, and that's going to kill your convection. If you have mid-tropospheric inflow of dry air, that's a very good way of shutting any kind of convection because you lose so much energy to that inflow.
So at an instant, there is some width of the front that is comparable with the net direction. I mean net dimension, the width of the front that is propagating.
The width of the there is a planetary scale. There is a moisture gradient to go back to the previous talk. This thing is propagating in moisture gradient, but as you get into the region where there's little moisture, the convection shut off, and that's of course one of the key issues. If you don't have the moisture, you don't have convection, and so that's what will happen. Another very interesting thing that happens is that it looks like as the system dies off, very often we see that other system shooting back in the other direction. So the system goes in one direction. It dies off, and it looks like actually there is some kind of reflection, which actually the very idealized model can show this kind of reflection. I'm not sure that's the explanation, a full explanation here, but there is some complex. This kind of shooting reflection is kind of a very funny behavior.
Thank you.
Yeah, in fact, these animations are very fascinating. One question I have, do you get any organization of this on MCS type, or it just tries to overshooting individual plumes rather than any organized convection in this case? You know, all the time what I see is just simple individual cumulonimbus towers rather than any organization of the scale of what you see in nature, like MCS.
That one.
Yeah, but animation, actually when you see the animation, you don't get that. You know, what you actually
I can
find
show you
is
the animation, but I'm not sure. So.
Okay.
I would
anyway,
be happy,
that we can discuss later. But that is the impression I get.
Yeah.
That,
so this one is kind of it's a weird system because it's actually we talk about a synaptic scale score line. I mean,
right.
it's a monster.
Yeah.
Yeah. Hopefully that never happened in reality because it would be pretty painful to get through that. But this guy looks much more like basically an envelope of a convective envelope with embedded smaller score line and moving in the opposite direction. So I think that's some of that structure. Now I don't know if they look at all like what you see in the observations, but they do exhibit quite a bit of structure over there.
Okay.
And this is essentially a stratiform anvil. This is the cloud top temperature. So you see the stratiform anvil over there. You just need to get used to look at entropy. Yeah.
How does this your idealized simulation agree with the simulation which was produced by the Japanese people on their big computer? So they have also got.
Yeah.
So how do they look alike in the actual nature? Because that was a kind of produced in the actual nature.
So I mean, they have a much bigger computer than we do. So their simulation is much more fancy, Bell and Whistle and so on. I mean, they have a lot. I haven't looked at their simulation, so I don't know.
Let me make an obvious comment. Here we have no rotation. We're literally right at the equator. All the other serious simulations have beta and automatically have large-scale state symmetry. Here we don't. But we do have intraseasonal variability with a suppressed and active phase.
I have to say, if I can, one thing. I mean, the simulation that the Japanese are doing and the super big simulation are very nice. They're very hard to analyze. This simulation is something at the scale we can run in a couple of weeks on a small supercomputer. and we can analyze and so on. And I think there is advantage of doing some of these things to try to understand the basic concept of what we need to do, which is more what we're trying to do than try to get the most realistic simulation we could. So I think it's maybe a different approach.
It brings out very clearly that all kinds of parameterization which we are doing is not going to give you answer. They are all unrealistic. They say this is doing something very different. You have to resolve clouds.
Well, I would argue the other way. This is a fantastic test bed for trying parameterizations for clouds.
Yeah.
I would say. So, in particular, we're going to test the stochastic multi-cloud model on its capability to parameterize this cheaply.
Okay. So maybe we will continue the discussion during lunchtime.
Thank you.
Okay. Yeah, thank you for both the speaker for keeping at the time.